Good afternoon, everyone. My name is John Hurley. I'm an engineer at Netfilter, and in this talk, I want to talk about offloading Open vSwitch, and more particularly, offloading the kernel datapath of Open vSwitch to a SmartNIC. And in doing this, I want to focus really on two areas. Firstly, Conntrack within this, and secondly, how we can offload Conntrack, and how we can do this kind of in harmony with the upstream kernel. So, as I already mentioned, when I talk about offloading here, I'm talking about the kernel datapath of Open vSwitch. So, in turn, when I mention Conntrack here, I'm speaking specifically about Netfilter Conntrack. So, the contract that exists in the core Linux kernel, not the DBDK variants or anything like that. So, I'm going to start by giving an architecture that we have already implemented that can do this offloading. I'll show some results on that and kind of give an overview of why we want to do this offloading in the first place. But that's kind of not the conclusion to the whole talk. From this, I want to evolve the story and show how we're trying to change this architecture, and we're moving along with other vendors in this area to try and have a kind of open source way of offloading both the Open vSwitch data path and hopefully in turn how Conntrack offload will fit into this. So I'll finish by then giving an example of some kind of off-the-press, cutting-edge work that has been going on in the area of Conntrack offload within the Linux kernel, and try and give some of the possible benefits of doing this. So, first slide here shows a kind of high-level overview of how Open vSwitch in the kernel interacts with Netfilter Conntrack and how these link together. So a packet can come in off a NIC. It will go to the OVS kernel data path. We will try and do a match here. If we can't do a match, we may have to go to user space, get a match, and then that rule will be written down to the kernel data path. Conntrack comes into this as both a match and an action. So we can't match in Conntrack fields until we have the data, and we can't get the data until we have Conntrack as an action, as it were. So in this case, a packet may come in, it may match in the kernel, it may hit an action to say, go to Conntrack, get some information on the state of this packet. The packet will go to Netfilter Conntrack, we will do our lookups here, do some other processing, maybe apply NAT, do helper checking, all the stuff that was discussed in the last talk. We'll then apply this state data to the packet as metadata. The packet will recirculate back, come back into the Open vSwitch kernel module where we can do another lookup. Again, this time the lookup can actually match on some of this state information. We can use this state information to make an overall decision on what to do with the packet, output to a tunnel, send to a VM, whatever we may want to do. So how do we offload this? This is one architecture that we have already implemented, and it kind of adds like a third tier to this hierarchy within OVS and within the kernel of OVS. So a packet now comes in to our SmartNIC. We try to do a match here. If the rule doesn't exist or we can't match in a SmartNIC, the packet goes to kernel space. Same things apply that it tries to do a match in the kernel. If it can't match here, the packet will then go to user space, and again we'll be able to maybe do a match here. If we can match in user space, the rule will be written down to the kernel, and in turn this will filter down to the SmartNIC. So Conntrack entirely exists within this model on the SmartNIC. The Conntrack table itself, instead of being in the kernel, is now in actual DRAM on the NIC itself. So if the rules exist, a packet can come into the SmartNIC, can match, can go to Conntrack here, can do Conntrack lookups, get all the information that would happen in the kernel, recirculate still on the SmartNIC, and produce the final action. If, however, the packet then matches in the kernel and in kernel space, instead of going to Netfilter Conntrack, we kind of have our own module that we've put in here. It sort of steals the packet, extracts the tuple information that's required for Conntrack, and sends a request to the SmartNIC to have Conntrack carried out in the same place as anything else. So to have this one kind of area where Conntrack happens. The SmartNIC will then reply with the state information about this packet, and the packet will circulate back through the kernel as per normal. So a kind of problem with this view is that firstly we have to create our own custom kernel module that we insert in here to steal the Conntrack packets, as it were, and also to offload the rules in general. we have to apply our own patches to the Open vSwitch kernel module, recompile and load the new updated kernel module, which again isn't ideal. But before we move on to that, I'll kind of show what we can do, or what's the point of doing this offload. These are some results. So these are kind of basic tests. We do have actually ways, we presented here last year, ways of which we can try and improve these results. But just for illustration purposes, I'll choose to show these. The bottom left shows the two rules that we apply for this test. Quite simple. Firstly, we basically match a packet that isn't tracked, so anything that's coming in to the SmartNIC or into the kernel. And we send this to Conntrack, and in this case, we also apply NAT. We recirculate the packet, and this time we should be able to match on some connection state data and output the packet. If we look at the graph on the left, we should see the red bars represent the throughput we achieve with this offloaded Open vSwitch approach. The blue lines are with pure kernel space, OVS, I think it's 2.6. If we look at maybe some of the smaller packet sizes, you can see that effectively we are able to double the throughput achieved. Further justification for this approach is in the right diagram, which really shows the CPU usage that our server has had to apply to achieve these results. So again, the red represents the offloaded approach. And well, rather than showing the CPU usage, this is kind of showing the percentage of the CPU that is still free to go and do other things, to run your VMs, to do NFV, whatever you may want to do. So with our offloaded approach, as kind of expected, we have about 99 to 100% of the CPU usage and the server resources still available to us. To achieve the results shown in the left diagram, when we're running pure kernel space OVS, it's taken about 50% of the CPU resources to achieve these speeds. And again, this is a decent enough spec server. There's about maybe 40 threads running here. So this is kind of justification for why we want to do this offload. But as I said in the previous architecture, we kind of have this issue where we have to add our own custom modules, where we have to apply our own patches to Open vSwitch, recompile. We would like a way really to do this in a kind of open source, almost plug in and play method within the Linux kernel. So within the community and between ourselves and other vendors, this approach has kind of been settled on. This utilizes TC and TC Floor to try and do the offload for Open vSwitch. So for those who know Linux, may associate TC with packet scheduling and really egressing packets, but TC also allows the ability to apply ingress hooks to ports. And we can use this floor, this filter mechanism for TC to then add filter rules to these incoming ports. So the TC floor rules will be covered probably in more detail tomorrow, so I'll not dwell on it too much, but they can effectively do similar things to the Open vSwitch kernel datapath, can match to certain packet fields and generate actions. So the idea here is that the OVS user space, as of experimental in 2.8, can now be set to, when it tries to write a kernel datapath rule, it will first see if it can write this rule in TC Floor. If it can write it in TC Floor, it does. If it can't, because maybe something's not supported yet, it still has the Open vSwitch kernel path. So when you think a packet then can come in off the NIC, it can, first of all, will try and match these TC Floor rules. If it can't match there, it still will go to the Open vSwitch kernel, try and match there. If not, then it will go to user space. So why do we want this TC Floor? Why is this of use? Simply because TC Floor already has hooks in the upstream kernel that allow for the offloading of rules. So effectively, we can write our own driver, which we have, which is also in the upstream kernel. If anyone wants to go and look at it, it's called NFP, which can register to offload these TC Floor rules. So when we run this setup with OVS-TC, as it were, the rules that are written to TC Floor can effectively be written straight to the SmartNIC without any changes to any code in the upstream kernel. So Conntrack, where does it fit into this? At the minute, it doesn't, but hopefully very soon it will. So I think there was a talk at NetDev last week or the week before where people are starting to give ideas about how Conntrack can fit in with TC Flower and where we can go from here. This is kind of the way I've described it here, and I think from the feedback I've been hearing, this is kind of the way things are going to go, where Conntrack within TC Flower takes a similar stance to that of the Open vSwitch kernel module, whereby Conntrack itself is both an action and a match field. So we match, we send to Netfilter Conntrack, we recirculate, then we can match on the state information. So hopefully this kind of architecture is something that we will be looking at in hopefully the coming weeks, if anything, whereby we can offload not only our TC Flower rules, but hopefully our Conntrack rules. So if we kind of look at the arrows I have on this diagram, TC Flower to the SmartNIC, to the NFP, that exists. Open vSwitch kernel to Conntrack module, that exists. That's been there from OVS 2.5. This new work will hopefully exist quite soon, going from TC Flower to Netfilter Conntrack. But we also have the line from Conntrack to the NFP. So how can we offload Conntrack flows? This is something that doesn't exist currently, and it's something that we've been looking at, and hopefully, again, very soon will exist. So at Neternome, we've been doing some work the last few months with Pablo Neira, who you may recognize as maintainer of Netfilter and NF tables, and by and large, Conntrack. A couple of weeks ago, there were some RFCs posted that describe changes that can be used possibly, or hopefully, to offload Conntrack. So I've kind of stole a quote from Pablo here to describe what's going on, and it simply says that we're not offloading Conntrack, but we're offloading flows. Now, this seems a bit strange because I'm talking about offloading Conntrack, but by and large, they're the same thing. So to dig in a bit deeper, really what we're saying is that within Conntrack in kernel space, within Netfilter Conntrack, there will be this idea of a flag added to the connection state to say that this connection has been offloaded. So we know about this connection, we know it exists, but now something else is taking care of it. This means that then flows won't be timed out and a lot of housekeeping can be done. The proposal that we're putting forward initially is that flows are not offloaded until they reach the established state. So independent of the mega flows or whatever that Open vSwitch may create, the first packets in any unique 5-tuple flow will go via the kernel and via the Netfilter Conntrack module. Once we get the established state, then we can decide if we want that this flow can be offloaded, mark it as offloaded, and let the NIC or the underlying hardware device take over and continue here. So why this approach? What are the advantages of doing it this way? Why not try and offload everything in Conntrack? Well, first thing, the kernel and Netfilter Conntrack within the kernel still gets to make a lot of the key decisions. So obviously from a SmartNIC perspective or an offload device perspective, this lessens a lot of the kind of code complexity that we have to offload. But there are also other advantages to it. So Conntrack itself in the kernel still gets to decide when a flow has become established. It still can track, say, TCP handshakes, whatever else we may need to do. And we get a lot of other kind of logic for free. So one good example here is the IP address selection if you're looking to do NAT via Conntrack. So it's not as simple as just picking a random IP address from the range. We need to be sure that this tuple hasn't been used before. Maybe flows from the same FTP session are all mapped to the same NAT address. So a lot of that comes for free if the first few packets go via the kernel. I've also said that we're not restricted necessarily by the SmartNIC resources, and maybe put in quotes here because it's not true, but I said we can support unlimited flows. What I really mean by that is that if our hardware offload device has sort of X amount of memory and can store N Conntrack flows, well, that doesn't mean that N is necessarily our limit, because we're still bringing the kernel into this. If we, for example, fill up all our hardware entries, we can still let flows pass through the kernel, still be tracked correctly, and then maybe if flows start timing out on the hardware, we can choose to offload them at a later stage. Another important point with this is that offload is not necessarily transparent here, so it's not happening without the user knowing. This is something when we first broached this idea with the Netfilter community that was something that was very important to them. Basically, that if people wanted to run Conntrack or were running something that specifically used Netfilter Conntrack, then they specifically wanted Netfilter Conntrack to be used almost bit for bit as what it does. So we can't just say that we're doing Conntrack here if we're not doing exactly what they expect. But this way, Netfilter Conntrack within the kernel is still getting to make a lot of these decisions, so there shouldn't be a problem here, certainly a lot of the initialization decisions. And secondly, we're actually saying that this flow has been offloaded, and not only that, the user, be it someone writing TC rules or OVS itself, can specifically decide when a flow, at what point a flow should be offloaded. So there's a lot more visibility here. And finally, compared to our previous architecture that we showed, we have a nice kind of synchronization here between the entries that exist in the kernel contract table and those that exist on the SmartNIC. So everything that is being tracked on the SmartNIC, it will be known about in the kernel. Maybe we can update statistics here and keep things relatively well synchronized. So at least if we're going to run things like contract D or something else from user space, we will still know about all the flows that we're tracking in this area. So this is kind of new stuff. The RFC, as I say, has gone out a couple of weeks ago. It's not necessarily 100% confirmed. It still is an RFC. If other people have any views on this or think it's a complete no-no or there's another way we should go, we'd be very interested in speaking to you and hearing. But hopefully within the coming weeks and months that this approach will take off and we will have a kind of upstream way that, similar to what we're doing with OVS and TC, that we can incorporate Conntrack offload into this. And yeah, I think that's a good note to finish on. Just as a final slide, I was asked to show this from the OpenNFP guys. For anyone who's interested in the Data Acceleration Developer Day, in a couple of weeks, the information's here, and you can check out their website. So,
let's thank our speaker.